This is a recap of the t-test workshop, where we are looking at two data sets. We have old patient response to old drug and patient response to new drug. The question is the new drug any better than the old drug? The way we're going to do that, answer that question, is by finding the minimum and maxima for each data set, calculating the frequencies in order to generate a histogram, plot the histogram, comparing old and new drug data, and make a hypothesis. Are they different? And then, using data analysis, actually put some numbers to that by performing a t-test. So the first thing we need to do is work out the minima and maxima. So this is recalling functions from previous workshops. Equals min equals max. Every function follows the same format. So we have equals, function name, brackets, and then data. What we can see already is that the range of the old drug compared to the new drug is shifted. It's getting a better response, which would suggest that maybe the new drug is better, but we're not really sure yet. Next thing we need to do is calculate a histogram, and this is done by setting up your bins. This is why we worked out the range. So I've gone for slightly lower, all the way to slightly beyond the highest value, in steps of 5 in between. And what I want to know is how many data points in this list fall into this bin here. So have a value between 10 and 15. I could go away and count them. I'm not going to do that. Instead, I'm going to use this function here. So the frequency, so equals frequency, brackets, data array. So that's highlighting all the data for old, comma, bin array. So that's the list of bins. And it's given me an extra data point here because it's trying to work out what to do with this 85 and up bin. We can do the same thing with our new data set, so frequency. Comma. Oops. And again, you can see there's a slight shift. Maybe this data is looking a little bit better. So next thing on our list, making a graph, highlighting the data of interest. Insert. Histograms traditionally are presented as bar charts, so let's not argue with history. I could, in principle, just click on the first option and then have to sort everything out, but that seems tedious. So instead, we're going to go to more column charts, and it gives you a bunch of additional options. You can see here, this one has our x-axis sorted out correctly. It's overlaid just the two data sets I'm interested in. So that's the one for me. And what we have is in blue, the old drug data, and in orange, the new drug data. Again, this suggests that the new drug is better. There's a bit of a shift to higher response values. My only concern is this bin here, where it might be artificially pulling the average to a higher value. So hypothesis at this stage, I'm going to say, yes, it's different. New drug is better. Next thing on your to-do list, you could, in principle, work out the mean, you could work out the standard deviation, you could work out the variance, and you could perform additional maths in order to calculate by hand the t-test. Or, this is a skills module, I'm trying to teach you how to do things well. You can click on data at the top here and go across to data analysis. And it should give you some options for t-tests. We've got paired to sample. That's where you know that you are looking at the same person or thing before and after an intervention. So if I gave somebody measured somebody's response, gave them a drug, and then remeasured their response, that's why I would use a paired t-test. On the other hand, we've got two samples or two groups of samples, assuming equal variance. I haven't calculated the variance here. We could, but since I don't know what the variance is, I'm unwilling to say that I think they're equal, which leaves me with two samples assuming unequal variances. So that's the one we're going to choose. Click OK. And variable 1 range, so that's your first data set. Variable 2 data range, that's the new drug. I haven't calculated the mean of each of these data sets. I don't want to put a hypothesis onto how different they are, so I'm just going to leave that blank. The important one for us is this alpha parameter, 0.05. This is the threshold for our p-value. P-values tell you about how confident you can be in your data. P-value of 0.05 means that you are 95% sure of your answer. So click OK. And it's generated for us a new sheet. I'm just going to make this bigger so it's easier to read. There we go. And we have Excel doing our work for us. It's calculated a mean. And yes, that reflects what we saw in our graphs. It's always good practice to look at the data first and check that the numbers that you get out do in fact make sense. So 54 versus 49, that seems sensible. Variance, there is some difference in the variance there. Each of our data sets had 100 patients in them. And DF is the degrees of freedom. Degrees of freedom is the combinations of samples. So we had 100 minus 1 possibilities and 100 minus 1 possibilities. So that's 99 plus 99, which gives us 198. And then the thing that's important for us is our p-value. P-value is telling you whether or not the data is statistically significant in its difference. And what we have is a p-value of 0.00009, which is lower than our threshold of 0.05. So we can say with some confidence that the two distributions are in fact different. This kind of analysis, the t-test, can be applied to any data set where you are comparing two populations. If you want to compare between more, then you're going to have to do what's called an ANOVA, and that's a different workshop entirely.